Hi there. So today we're going to be continuing our series based on the integrals in chapter 1 of the book Almost Impossible Integrals, Sums and Series by Cornell Eoin Verlaine, whose name I was indeed butchering as I'd mistaken the I in Eoin for an L. I'm still not convinced I'm pronouncing that correctly, but if anyone wants to give me a hand with that, please feel free to do so in the comments below. That being said, let's jump straight into it. Okay, so the integral we'll be evaluating today is actually a pair of integrals. These logarithmic integrals just here, and at a glance they appear to be identical, but they're actually different in an important way. And just so you can see, the limits are different. The limits on the integral I are from 0 to 1, and the limits on the integral j are from 0 to a. So the upper limit on j is a bit more general, where a can be any real number. Okay, so well, we might as well just jump straight into it. So we write I, oops, please excuse me, we write I is equal to, well, it's equal to the integral, oh Christ, that's not good, right, sorry, just trying to figure out the positioning of my little tablet. The integral from 0 to 1 of x to the m times the natural logarithm of x to the n dx. Now, I think you can see here we have two integers, m and n, so we're going to write m, n are positive integers, which maybe I should have specified before. So in that case, it makes sense to rename this integral I m comma n. So this integral is indexed by the two integers m and n. So really it's an infinite number of integrals all at the same time. Now for integrals like this, you might notice, well, I think it would be maybe nice to try using the method of integration by parts, because we have a logarithm here, and when we differentiate it, it becomes a bit nicer. It becomes 1 over x, and this x to the m, well, it's very easy to integrate, so let's just get started with that now. Well, I think we can agree that another way to write x to the m, is as the derivative with respect to x of x to the m plus 1 with respect to x. And of course, if I differentiate this, I'll pick up a factor of m plus 1. And to get rid of that, I'm going to insert a factor 1 over m plus 1. So what we're going to do is we're just going to substitute that into our integral. So we write I mn is just, well, we have 1 over m plus 1, the integral from 0 to 1 of the derivative with respect to x of x to the m plus 1 multiplied by the, or let's say, sorry, the natural logarithm of x all to the power n, and we're integrating that with respect to x. Very good. So what next? Well, we just use integration by parts because we have the derivative of something here, and we have another innocent bystander function here multiplying it. So we write, well, if I just remind us what the method of integration by parts says, it's a consequence of the product rule. So if you just write the product rule, so if you write that, let's see, so we have a function uv, and we're going to write its derivative, so we'll write uv prime. Well, that's just the same as u prime v plus u v prime, and then what I'm going to do is I'm going to integrate both sides, and let's say integrate it from a to b with respect to x. So this is a notation that I feel seems to be less common. It was actually a lecturer at undergraduate that showed me this, and I've never really seen it anywhere since, but I really do like it. It's just that if I write an operation here with a colon, it just means I intend to do that to both sides of the line that came before. So I intend to integrate both sides with respect to x, and I want the definite integral from a to b. Well, if I do that, this is a derivative, so I just undo the derivative. I take the antiderivative, and I evaluate it at both limits. So I write uv evaluated from a to b, and I want to write that's equal to, well, just the definite integral from a to b of uv prime plus the definite integral, oops, please excuse me, that's u prime v, important I chose that order deliberately, and I write u v prime with respect to x, and that's also the definite integral from a to b, okay? And of course, what I do is I just shift this to the other side and make the integral from a to b of u prime v. I make this the subject, and just to make that a bit more obvious, so I want this to be the subject. Well, if I do that, I'm going to wind up with the integral from a to b. Let's make ourselves a bit more space. The integral from a to b of u prime v with respect to x. That's just the integral. Well, we have this, right? So we have the uv evaluated from a to b, subtract the integral from a to b of uv prime with respect to x. So you can see what's happened here. We have some constant here, which we evaluate based on these functions u and v, and we swap the differentiation. So we're no longer differentiating u, we're differentiating v instead. So this here is what we call integration by parts. Integration by parts. And so let's go back to our integral. We go back to our integral I mn. Well, we use integration by parts, so we write 1 over m plus 1, and we take our u, which is x to the m plus 1, and our v, which is log x, natural logarithm of x to the n, so we write x to the m, the natural logarithm of x, and this is all raised to the power n, but we evaluate it between the limits, and our limits of our integral were 0 to 1, and I think you can probably see what's going to happen there, but we'll come back to that after we've written this. We end up with the integral from 0 to 1 of x to the m times the derivative with respect to x of the natural logarithm of x, all raised to the power n, and this whole thing is of course integrated with respect to x. Now, looking at this, I think you can see what's going to happen. If we evaluate the logarithm at x equals 1, we collect 0, and if we evaluate x to the m at x equals 0, we collect 0. So at both limits, this product vanishes. And then, well, we can kind of massage this a little bit, because I think you can see what's going to happen is we have to use the chain rule to evaluate this. So we'll come up with n log x to the n minus 1, right? And then we'll pick up a factor, the derivative of the inside, which so we'll pick up a 1 over x. And of course, please excuse me, this should be to the m plus 1, and this should be to the m plus 1. Not that it makes a difference here, but this should be to the m plus 1 because I picked the derivative off to the m plus 1, and I did forget our little factor of 1 over m plus 1 as well over here. Very good. So now we can just, well, perform our simplification. That's equal to minus 1 over m plus 1. And looking on the inside, that's the integral from 0 to 1 of x to the m plus 1 times, just as we promised, n, the natural logarithm of x to the n minus 1, and of course we have to differentiate the inside as well, so we have a 1 over x, and this is with respect to x. And it's easy to see the simplification here. We cancel one of the x's with this x here, okay? And here, or we have a factor of n on the inside to pull outside of the integral. So that's minus n over m plus 1, the integral from 0 to 1. And remember, we cancelled one of those factors of x, so we end up with x to the m. But now we have the logarithm, the natural logarithm of x to the n minus 1, and that's integrated with respect to x. Now this is important because I want you to compare this, I really want to compare this to our initial integral. Now I called our initial integral Imn because it depended on the indices m and n, but this seems to be the same integral as if we indexed it with m and n minus 1. So really this is the same integral, but Im n minus 1. So what we seem to have here, what we seem to have come up with was some kind of recurrence relation, okay? And in the business of integrals, this is called, in particular, a reduction formula. A reduction formula. The name's not important, but just in case you hadn't heard the terminology before, this is a recurrence relation. And what do we do with recurrence relations? Well, it seems m is left intact by this recurrence relation. So the good news is we only have to worry about stepping through one of these indices. We only have to worry about stepping through the index n. We only have to worry about stepping through the index n. Okay, so that means we can ask the question, well, this essentially, well, if we just kind of say what this is telling us, this is telling us the next integral in terms of the previous, right? So it stands to reason that if I know the first integral, then I know all of them because I can work out the next one and the next one all the way until I count up to n. Now, n is arbitrary, so how are we going to do that? Well, you know, in mathematics, like I could sit here and explain, but it's often better just to write something down and go off a hunch. So our hunch is that if I know the first integral, I know all of them. So it stands to reason that I want to work out the first. And we start counting in maths whenever we can, more so in computer science, but in maths we start counting from 0 wherever we can manage it. So I'm going to, please excuse me, we're going to write I0, and we're going to write the definition of I0, that's the integral from 0 to 1 of x to the m, the natural logarithm of x to the 0 with respect to x. But of course, anything to the 0 is 1. And I think you can see now, why I chose the bottom index as 0 instead of 1, because this simplifies the integral to the point where it's trivial. And I won't insult your intelligence by stepping through this. I think you can see that this integral is just nothing other than 1 over m plus 1, right? So we've done this integral here. Well, we have the bottommost one. Well, what's the next one? I would quite like to know Im1. And you might be thinking this is useless because I want the integral in the general case, but please just stick with me and we'll see kind of why we're doing this. We're looking for Im1. Well, the rule here tells us that if I want the next integral, I have to take the next number divided by m plus 1 and multiply it by the previous integral, not forgetting a factor of minus 1 in front. So we write minus 1 over m plus 1 times the previous integral. The previous integral is Im0, which is 1 over m plus 1. And so we don't forget where we got that from. I really want to be very clear about the fact that this is nothing other than Im0. This is the previous value of the integral. Next, let's simplify it. It makes sense to simplify it. So we write minus 1 over m plus 1. And now I think it's worth talking about what the strategy is here. What I'm going to do is I'm going to evaluate enough until I can see some kind of pattern. Okay, so I'm hoping I'm hoping there's a pattern here, okay? And once we get maybe up to the third integral we've written down, we'll say, look, that's enough. And then we're leaving just enough space here to write our final answer in its most general form, okay? So we will ask for the next one, IM2. Well, that's just going to be minus 2 over m plus 1 times the previous integral, and the previous integral is here, right? So we're going to get 1 over m plus 1 squared, and there's a minus sign that we don't want to forget about, so we'll include it by turning this minus into a plus. And of course, we'll take one stage of simplification. We'll write that as 2 over m plus 1 cubed. And of course, I stress that this guy here is IM1. Okay, so it's the next, it's the previous integral. And let's just see if we can see a pattern when we do one more. I think anyone who's used to this kind of calculation can probably see that maybe there's a factorial involved, maybe there's a minus 1 to the n involved, but we won't spoil the surprise. We'll just keep going. So we write 3 over m plus 1, and then we just pull this factor in. So we have a 2 over m plus 1 cubed. And again, we do the same thing we did before. We just put some simplification and we write minus 6 for the 3 times 2 all over m plus 1 to the 4. That's the cube plus the 1. And I think maybe we have enough now. I think for me, maybe it's ill-advised, but you can see here this is our next integral again, just to keep ourselves going. 2. Well, really, let's try to see what pattern these guys follow. Well, I can see minus 1 to the 1 here for the minus 1, and I can see a minus 1 squared here for the no minus, right? And I can see a minus 1 cubed here, and I can see a 1 factorial over an m plus 1 to the 1 plus 1, and I can see a 2 factorial. I can see a 2 factorial over m plus 1 to the 2 plus 1. You can see what I'm doing here. And that's going to be a 3 factorial. So 6 is 3 times 2 times 1, which is 3 factorial, times m plus 1 to the 3 plus 1. And I think you can see what the pattern's going to be. I think you can see the pattern is that for IMN, oops, please excuse me, IMN, what we're going to collect is minus 1. We're going to collect minus 1 to the n times n factorial all over m plus 1 to the n plus 1. And this is our final answer. Now, remember, what we've done here is kind of like heuristically come up with the answer. We've played a game. This doesn't seem legitimate until we realize that the pattern has to hold. I'll tell you why the pattern has to hold, because every time to get the next one, to get IM4, what we have to do is we have to multiply the numerator by 4, and that will always turn the previous factorial into the next factorial. So 3 factorial times 4 factorial is 4 factorial. 4 factorial times 5 factorial is, 4 factorial times 5 is 5 factorial. And in fact, in general, m factorial times m plus 1 is just m plus 1 factorial for any particular value m, right? Or k, maybe I should say, for a general number that we haven't used here at all, right? And of course, we're multiplying in another minus sign, so we're always going to have, another power of minus 1 going in, and we're always multiplying another factor in the denominator of m plus 1, so we're always increasing by 1 as we go up. So normally what I think the facetious way to do it would be to take this formula and prove by induction that it satisfies this recurrence relation, but actually we don't need that to be, we don't really need to go through that, because we can see by inspection that it has to, because the rule, essentially this follows quite nicely the rule for generating the next term. So maybe we didn't even need to do all this work. I think if we'd been a bit more clever, but perhaps I'm not that clever, I had to, whenever I do these problems for the first time, I always have to write tables out like these and do the comparison and see what happens. So really here, we can box this up because this is our first integral. We have I, m, n is nothing other than minus 1 to the n times n factorial divided by m plus 1 to the n plus 1. Very good. So now we can look at j, and at first you might be thinking, well, you know, I looked at this integral. This integral wasn't hard at all. This was easy, right? I think you'll probably see in a second that there's a teeny bit more to it. Not much more, but enough that we would need to think about it carefully. I think so. Let's write the integral down. So j is just the integral. It's the same integral, but with different limits from 0 to a of x to the m times the natural logarithm of x to the n with respect to x. Now, here I think any sane person would probably immediately try to change the limits instead of from 0 to a to 0 to 1, because then we'll have reduced the problem to the integral that we've already computed, okay? And that will get us far, but not quite all the way there. So let's first start by saying, of course, I think you understand that we need to index this integral by m and n again. And then we're just going to write, well, what are we going to write? Well, we want this upper limit to be a, so we're going to define a new variable that is our current variable divided by a. Now, instead of going through the pain and grief of doing that, I think, you know, as a physicist, I've kind of, well, now that I'm a physicist, I kind of do these awful things that maybe I would have screamed at other people for doing in my younger days, but now I'm completely fine with just going ahead and noting that, well, if I put an a to the m plus 1 on the outside, we have just enough x's, we just have just enough factors of a to multiply in to take over all occurrences of x that are outside of the logarithm, and you'll see what I mean when I write that in a second. So 0 to a of x divided by a, x divided by a to the m times, and I'm going to put here, the natural logarithm of, well, it's a times x over a, right? Because I want this new variable x over a, because we intend to divide the limit by a, right? Because 0 over a is going to be 0, and a over a is going to be 1, because we want our limits to be from 0 to 1. And of course, we write the derivative, well, sorry, the differential dx over a, because we pulled in m plus 1 factors of a. We used m of them here, and we used 1 of them here, and we didn't need a factor inside the logarithm. Of course, we understand this is to the n, right? All very good. So now, I want you to think about this for a second, but this integral is the same as the integral from 0 to 1 of x to the m, excuse me, times the natural logarithm of ax all to the n with respect to x. And one way to think of this is I could change the variable to u. I could write u is equal to x over a. You know, I could do my differential, I'll pull out a factor of a, then I do this, and I pull out another factor of a to the m, and then I'll get the same result here. But this result enables you to do this way of thinking about it. For me, I wouldn't even write this intermediate step here, because it helps you think about how to do this in your head, just to really quickly make the substitution here. So I hope that's just well, I know, I suspect maybe it's something everyone does probably. Maybe I'm just being a bit silly by spending so long talking about it, but I think you can see that this is just a nice way to make very simple substitutions in your head without having to go through the pain and grief. Because I could convert to u, then because it's a definite integral, this is a dummy index and no one cares what it actually is. So I'm within my rights to change it back from u to x, and it's the same integral. Okay, so from here to here, this is, of course, please understand, the same integral. I've just changed the variable. Okay, very good. So now I'm going to write this is a to the m plus 1 times the integral. Now you might think we're done, but this ax is is our worry here, and I'll show you what to do about it. That's x to the m times, well, we have the natural logarithm of a plus the natural logarithm of x. And I think you can probably see where we're going with this. This here is kind of like a binomial, something we can expand as a, well, it is a binomial, so we can just expand it. So a to the m plus 1, the integral from 0 to 1, x to the m, and we write this as the sum, and we need a new index. We used m and n, and I like k for indices in sums. So k from 0 to n of n, choose k, and we write the natural logarithm of a, and that's to the n minus k times the natural logarithm of x, all to the k, and this is all to be integrated with respect to x. And now I think you can see what's going to happen, because this n choose k and is a constant, right? Doesn't depend on x, and a is a constant. This was the upper limit, so of course the natural logarithm of a has to be a constant as well. So this whole motif just comes out of the integral, and we write we don't worry, because we're physicists, right? We don't worry about these problems with exchanging in the order of summation and integration. So we sum from k is equal to 0 up to n, and we take out that n, choose k, and we take out the natural logarithm of a to the n minus k, and then we integrate from 0 to 1 x to the m, the natural logarithm of x to the k, and we're integrating this with respect to x. But we've seen this before. This is the integral from 0 to 1 of x to the m log x to the k. This is just our initial integral, I, but instead of mn, we write mk, right? So this is our integral I mk, okay? And we're going to put it in, but I'm going to suggest that we're going to buy something. We're going to buy something for ourselves if we expand that n choose k. So n choose k is just n factorial over k factorial times n minus k factorial, and we take that the natural logarithm of a all to the n minus k, and this guy here, I think maybe we remember from before, is just minus 1, let me see, to the k times, I think it was k factorial divided by, what was it? It was m plus 1 to the k plus 1, okay? So now we're just going to cancel well, this is why we did it, because we expanded this and we remembered we're going to have a k factorial here. So we can cancel those factors of k factorial. Now, I think you can see it's all going to come together quite nicely, and I think people often like having minus 1 to the k's as far to the left as possible. So I'm going to rewrite this. I'm going to rewrite this as a to the m plus 1, the sum from k equals 0 to n of, and we write minus 1 to the k, and we multiply that by, let's see what we have. We have our n factorial times the natural logarithm of a to the n minus k, all divided by m plus 1 to the k plus 1. And I think if we're a bit there we go. I've forgotten something again. Please forgive me. So maybe I shouldn't have been so quick to do this. But what I'm going to write is this guy here. This guy here is otherwise known as NPK. Okay, so n choose k is the number of combinations of k things taken from n things. NPK is the number of permutations of k objects taken from n objects. Okay, there are other ways to kind of think about this. It's a combinatorics problem. You don't need to worry about this, but this is just a notation. This guy here, just please understand that just in the same way that n choose k is n factorial over k factorial n minus k factorial, this is just another name for n factorial divided by n minus k factorial. Okay, very good. So now we have just this guy left over. So we have the natural logarithm of a to the n minus k, all divided by m plus 1 to the k plus 1. And this is our integral I. Oh, sorry, please excuse me. That's not I, that's j m n. And this is our integral j m n. And this is our answer. And I'm not even going to try to say this out loud because it's a sum over some quite gnarly looking things right there. But this is the result. Thank you so much for listening, and I hope to see you again next time.